Now, we are going to explain the mathematical procedure for the input-output transformation. Let's just say we are using a simple queuing system. You can imagine MM1 queue. However, for MM1 queues, we can have theoretical results, so the simulation is not a necessary mathematical modeling approach. So we can, for example, think about a little complex queuing system, just as we have seen in our arena applications. Now, actually, a simulation is trying to find the expected value of a function of a random input. So I'm going to explain that to you. Now, let's just say we have input variables collected from the original system, and these input variables follow certain distributions, certain probability models. So all of these input variables are collected in this vector X. So this is a vector, and it contains maybe a very, very large number of random variables. Okay, for example, for a simple queuing system, the inter-arrival time of the first client, the service time of the first client, the inter-arrival time of the second client, the service time of the second client, so on and so forth. So for every client, that X vector contains the inter-arrival times and the service times, but as a random variable. Okay, so that's a vector. Because of that reason, we are using bold notation, because in mathematical studies and articles, you'll realize that most of the vectors are written in bold. The random variables are written in capital. The vectors are written in bold. Because this is a bold capital letter, this means X is a random vector with random components inside it. And D is another vector, but it is actually controllable or partially controllable decision variables. So in every system, there are some input variables that you do not have any control over. For example, the inter-arrival times of the customers. But there are some variables which you have complete control or partially control over. So these are the decision variables. And we denote them by D. So X are uncontrollable input variables, D are controllable input variables, and Y is the output variables. For example, the length of the queue at any time, or the time that the entity is spent in the system. So Y are the output variables. Again, it is a vector, and it's a random vector because we have random inputs. The outputs are expected to be random as well. And F here is an input-output transformation, which is the black box of the simulation. So here F is what? F is the model that you create. F is the input-output transformation. It's a very, very complicated function. Because it is very complicated, you cannot explicitly define it. You need software such as Arena to express that function. So F is a very, very complicated function. Even for a simple MM1 queue, it may be a very complex function. It can use maybe a very, very large dimensional integrals, which means nested integrals inside each other. You will not be able to solve. I mean, when even we are solving 3 integrals nested, we are having hard times, right? So F is a very, very complex function that involves with so many integrals. And because most of the functions that we are going to define are indifferentiable, because of that reason, that F cannot be expressed or solved explicitly. However, we know that simulation approach converts this random input to outputs by function F. Okay, F is the black box. So in literature, we call this function the black box function, which converts our inputs in your model to the outputs of the model. Now let's give an example here. The Fifth National Bank of Jasper. It says we consider an MG1 driving queue in a bank and its current state. Arrivals occur according to a Poisson process with rate lambda equal to 45 per hour. So driving queue in a bank. What does driving queue in a bank means? So you are going to go in a bank, but imagine now you are going there with your car, and just like you order something from McDonald's in a driving queue within your car, because you are going to eat it in your car, not in the restaurant. So you get in the driving queue, and this is a bank. You are, for example, taking a loan from the bank in a driving queue. I mean, it is interesting, right? I mean, without stepping out of your car, you can get credits or loan from a bank. So at its current state, the MG1 driving queue, which means the inter-arrival times of the cars are exponentially distributed. In fact, the rate of this exponential distribution is 45 per hour, which means 1 over 45 hours is the average time between the arrival of the automobiles. So it says Poisson process, which means if the inter-arrival times are exponential, then we say that the arrival process is a Poisson process, right? So when it says Poisson process, do not think that the inter-arrival times are Poisson. The inter-arrival times are exponential in that case. So that is the relationship between the Poisson and exponential distribution. And we have a general service time, and it is normally distributed with mean 1.1 minutes and variance of 0.04 minutes square. And the parameters are estimated using data sets. So we have observed 90 automobiles. For 90 automobiles, we have observed their inter-arrival times and the service times between 11 a.m. and 1 p.m. on Friday at rush hour. Everybody is coming there to take a loan in this Friday afternoon. I mean, nobody is hungry. Everybody is trying to take a loan from the bank. Okay, there is only one teller, therefore only one waiting line. So what are the improvement options for this system? We can install a computer terminal which may reduce the mean service time to 0.9 minutes. So one decision is this. Another improvement is we can increase the number of tellers. So instead of one teller, we can put two parallel tellers. And another improvement option is the number of waiting lines may be increased. So we can put separate waiting lines there. So we may have multiple queues for multiple tellers there. I don't know if it is a good idea or not. It's just a suggestion. So we have uncontrollable input variables in the system. What are these? The inter-arrival times and the service times. So inter-arrival times are given in X1, and X11, X12, X13 are giving us the inter-arrival times. So the first index stands for that it belongs to inter-arrival times, and the second index belongs to clients. Okay. So X12 means we are talking about the inter-arrival time of the second client. All of these are exponentially distributed with lambda being equal to 45, which means the average being equal to 1 over 45. And the service times are represented by X2, and X21 is the service time of the first client, X22 is the service time of the second client, so on and so forth. They are all normally distributed with location parameter mu, which is equal to D2. You know, right now the location parameter is 1.1, right? But by a decision, we can change it. Therefore, I'm just going to write D2 there because it is my decision variable. I know that by installing computer terminals, I can reduce this D2 from 1.1 to 0.9. And the variance is 0.04. I cannot change the variance because this is not an improvement option for me. And what are the controllable input variables? D1. Right now the number of tellers is 1, but we can change that. We can increase it to 2 or 3. Another controllable input variable based on the improvement options is D2. Right now it is 1.1 minute, but we can reduce this to 0.9 by installing a computer terminal. And the number of waiting lines is D3, which is equal to 1 right now, but we can increase the number of waiting lines as well. Now, of course, like in every system, we will have some output variables of interest in the system as well. So Y1 is the teller utilization, Y2 is the average delay, and Y3 is the maximum line length. So what is the teller utilization? It's the fraction of time that the teller is being in use, being busy. What is the average delay? It is the average waiting time in the queue for all clients. And maximum line length is the maximum number of automobiles that we observe in the queue, because we need to define a parking space, right? I mean, if the queue is too long, then the queue is going to extract outside the bank area, right? So because of that reason, we are interested in the maximum length of our queue during the simulation. And there are some secondary output variables which are in our secondary interest: the observed arrival rate, the average service time, the sample standard deviation of service times, and the average length of waiting line. So these are not important right now. I'm just going to write them. These are the output variables of secondary interest. So these are not performance metrics. However, we are going to use them for input-output validation. So we are going to check if the real system has the same type of output variables as these variables from Y4 to Y7. But the main performance metrics are Y1 to Y3. So basically, we have a black box algorithm, which is our simulation model, which converts these uncontrollable input variables x1 and x2, which are the inter-arrival times and the service times, and controllable decision variables d1, d2, and d3. So you see, I'm not writing d1, d2, and d3 in bold because these are not vectors, but x1 and x2 are vectors. Now we have F, the input-output transformation that converts our uncontrollable input variables and the decision variables here, D1, D2, D3, into the output variables, which are Y1 to Y7. So our input-output transformation or simulation function converts a matrix here and 3 different decision variables here into a vector of 7 values. So suppose some of the output variables were also collected on the same Friday between the same hours. So let's just say we have collected some output variables like from Y1 to Y3, okay? So these are called the system responses. So for the same day, for the same Friday, we have collected the teller utilization at that 2 hours of time where we collect the input data. We have also collected the average waiting time in the queue, which is 4.3 minutes. And the maximum line length is also collected. So for every output variable, Y1, Y2, and Y3 here, we have also collected Z1, Z2, and Z3 here. So these are the system responses collected from the original data. Remember now, I have told you that your data set for the input-output validation should be different. But the question here says that the same output variables are also collected on the same Friday between the same hours. Maybe the collection of the output variables should be another Friday with the same hours, but here the question says that it is the same time as the input data are collected. Now, when the model is run with the random variates that we collected from the original system, so we have developed a model, we have developed the input models, but instead running the simulation with the input models, okay, by generating random variates, we are going to run the simulation model with the exact input values, the data itself. So the inter-arrival times and the service time are going to be the same. Or again, I mean, in simulation, you can also use the replication of them. So you can use the distributions as well. Now, the simulation generated output values Y2 are expected to be consistent with the observed system variables, right? So the outputs that we have collected from the system Z2 was 4.3 minutes. On the average waiting time was 4.3 minutes. Now, when we run the simulation, the average waiting time in the simulation model should also be very close to 4.3 minutes, right? Now, let's just say we have run 6 statistically independent replications of the model. So we have developed our model, we have developed our input distributions, and by generating random variate from our input distributions, we have run 6 different replications for 6 different Fridays. So we have generated artificial history for 6 different Fridays of the same system, and we have measured the average arrival rate, Y4, for each of these replications, average service time for each of these replications in minutes, and the average delay in minutes again. Now, if you check that out, for 6 replications, the average arrival rates are changing from 53 to 40, and the sample mean of the arrival rate of these 6 replications, so it's somehow the average of the averages. So the average of the replications, but in the replications, we are also calculating the average arrival rate among the clients. So the average in that replication is calculated by calculating the inter-arrival times of each client, and by taking the average arrival rates among the replications, we are calculating the average of the averages for the arrival rates. And the sample mean here is for 6 values is 48.17, and the sample standard deviation is 4.72. Without needing a formal hypothesis test, I can say that 45, the actual input variable here, the actual input variable, the rate parameter 45, would be inside the 95% confidence interval developed for the average arrival rate. And therefore, I will say that most probably the input model that I have developed for the inter-arrival process is correct. Similarly, I can collect average service times, and it is going to be 1.09 on the average for 6 replications with a sample standard deviation of 0.02. And again, I can say that without needing a serious hypothesis test, the 95% confidence interval built for the average service time here is going to cover 1.1, which is the current average time. So therefore, the input models seem to be correct. So we are basically collecting the input variables here, y4 and y5, even though we write them in the output notation as y4 and y5, they are the input variables. Now, average delay y2 is a performance metric, and we have collected the average delay time for 6 replications, and these are here. And when we take the average of the averages, y2 bar is going to be 2.52, and it has a sample standard deviation of 0.82. Now, we need to run a t-test here, a hypothesis test with the t-test here, to check if the expected value of y2 is equal to z2, which is 4.3. Now, you remember, we have collected the output data. The average delay collected on the same day was 4.3. Now, the average delay distribution, can it have a mean of 4.3 or not? We need to check that with this formal hypothesis testing, which is a t-test basically. Okay, we are going to run a t-test, and we are going to say that we need to test if the null hypothesis can be true or it is not true. Okay. So if H0 is not rejected, we say that on the basis of this test, there is no reason to consider the model is invalid. So if you can reject the null hypothesis, now you have enough statistical evidence to show that your model is not valid. There is a problem with your model. There is a mistake in your model, and we can run a two-sided t-test here with a t-statistic. Remember how you develop the t-statistic. So this is a two-sided t-test. Why? Because the alternative hypothesis is not equal. If the alternative hypothesis is greater than or less than the value indicated by the null hypothesis, then this is going to be a one-sided hypothesis test. Now, T0 is the t-statistics that we collect, which is calculated by what? The average of the sample, and from that we subtract the right-hand side of the null hypothesis, and we divide it to the sample standard deviation collected from sample divided by the square root of the number of observations. So number of observations is 6 because we have observed the average delay time for 6 replications. It is therefore important to run replications in simulations, my friend, because if you want to make a validation, replications are needed. So in a single replication, validation may not be possible, or it should be a very, very long simulation. Now, we have 2.51 as the sample average. Actually, it's 2.52 here. It doesn't matter. I mean, this one digit does not make any difference. And we have 4.3 as the right-hand side of the null hypothesis, and 0.82 is the standard deviation of the 6 observations, sample standard deviation. And you know how to calculate the sample standard deviation, I guess. And square root of 6 here comes from the number of replications. My test statistic is minus 5.34. Now, we need to identify the critical value for the two-side t-test for a significance level of 0.05. Because it says two-sided, we need to take the half of this 0.05, which is going to be 0.25. So my degrees of freedom is what? My degrees of freedom is 5, not 6. We have 6 replications and my degrees of freedom is 5. And my t value, critical t value for half of the significance level is going to be 2.57 here, because we are going to use 0.025. So my critical value is 2.57, and the absolute value of my t statistic obtained from this t-test is greater than that value. So we need to reject the null hypothesis and say that this model is not valid. But what is the problem? We have developed the input models and tested the input variables, and the input model seems to be correct on the average. Actually, we have just tested their average, but we actually need to test their distribution as well. But let's just say the input models are correct. So the input models are validated. Maybe there is a wrong assumptions about the structure of the original system. So maybe we have not correctly assumed the original system as in the model. So what the model seems to be inadequate. So it is not sufficient for its prediction of the average customer delay. So it is not valid. So what type of revisions we can suggest here? When a car departs after taking the service, it takes a delay time for the next car to get into the service point, right? Now you are running this simulation, but you imagine when a car leaves the system, the next car immediately comes to that location and starts the dialogue. I think the automobiles, especially when they are taking off, are not fast enough, right? I mean, it takes some time to accelerate the automobile, right? So the model needs to be calibrated by adding a delay between one service ending and the next beginning. So when a service ends and that car leaves the system, it takes some time for that car also to leave the system. So there is a delay between the completion time of one service and the starting of the next service because of the taking off times of these automobiles, right? And that delay is considerable, I guess. I mean, maybe it is going to take 20, 30 seconds, right? One car to take off and leave, and another car to take off again and come to that point. So the second revision is what? When a car enters the system and finds teller window available, it still takes time for the teller to be available since the teller is busy with the walking client. So nobody tells this, but in that system where the teller works with the driving queue, there are also walking clients as well. So again, even though the car gets ready to get a service, the teller may be busy with other processes, unfortunately, but nobody tells anything about this. Maybe after serious observation or after asking to the end users who work in the system, maybe we should ask the teller about the job he is doing. Maybe when you ask it to the teller, they are going to describe that they experience some problems between the services of driving clients. So they have other tasks to do in between them. But they are going to tell you if you ask them, okay? So the model needs to be calibrated by including additional demand on the teller's time based on the service times of walking clients. Maybe we need to introduce walking clients in that system as well. So even if you want to have improvement decisions about driving clients, you need to think about the other components of the system which is affecting the behavior of the other queue. If there are walking clients who are trying to get a service from that teller, so teller is a common resource here for different queues. In that case, even if you just want to improve the driving queue, you also need to put the other queue in your model because it is affecting the other one. Now, after these revisions, again, we have run 6 replications. And after these 6 replications, the input arrival distribution and the input service time distribution is not changing, as you can see, because these are dependent on the input values. However, the average delay is going to be affected. And you see the average delay obtained in the 6 replications is 4.78 with a standard deviation of 1.66. Now you need to test hypothesis once again. Can the average of these delays, average delays in 6 replications, can it be 4.3? Actually, not the average of the 6 replications, but the overall average, overall expectation, can it be 3.4, 4.3? Now, just by looking at 6 replications, we can run a t-test with a 95% confidence level once again. So we can say that my t-statistic this time is going to be 4.78 minus 4.3 divided by the sample standard deviation divided by the square root of the number of replications, and it is going to be 0.71. And for two-sided t-tests, the critical value is again 2.57 for a degrees of freedom 5. because the number of replications is 6 and significance level of 0.05, and the absolute value of your t statistic here is less than or equal to 2.57. Therefore, you can conclude that there is not any evidence, statistical evidence, to reject the null hypothesis. This time, the model is a better representation of the original system, but you should also check the other output variables, not just y2 and z2. Remember now, we have three essential system responses, Z1, Z2, and Z3, and we have just run a statistical input-output validation procedure just for Z2. You also need to do that for Z1 and Z3 as well. If they are important for you, then you need to do them that as well.